Okay, so we're actually right on time. So let's continue with Gaga, who is telling us about certified compilers a la carte. And also, let's thank the speaker again and the welcome new speaker.
Okay, so I'm going to talk about how to make certified compilers more extensible and modular. So it's joint work with Jian, Ende, Zhao, and Yizhou from Waterloo. So certified compilers are a critical piece of software, and application developers who write the software in high-level language using the compiler to transform that code into instructions that the machine can understand. But there's a bug in the compiler. Okay. Now, this bug in the compiler. This completely invalidates application level guarantees. This bug in the compiler is completely invalidates the application level guarantees, right? And it's not just a hypothetical situation. Real-world compilers like Clang and GCC have open bugs. And one way to eliminate bugs in compilers is by proving it correct. Compilers that are proven correct are called certified compilers. And these compilers eliminate an entire class of bug in the critical parts of the software stack. Now, the problem is that certified compilers are not cheap. Aside from the inherent difficulty of constructing mathematical proofs, extending, maintaining, and evolving compilers are difficult. Certified compilers are difficult. And this is a real problem because as language evolves, the compiler needs to evolve as well. So to see this in practice, let's look at a real world, let's look at a toy example of a certified compiler. So let's build a certified compiler for IMP. The first thing we do, we have our source language, which is just a simple imperative language. So we have semantics for the source language. Then we give you target language, which is a stack-based virtual machine instruction set. We give semantics to the instruction set. And then we write a simple compilation function, which is a recursion over the source language. And then prove is correct. Now the problem here is that when we want to extend IMP with new features, for example, switch statements, loops, and heaps, we have to duplicate the code. And this copy and paste is antithetical to good engineering practices. Now it creates tedium, obstruct changes, and collapse separation. And this is not just a new problem. It's an old problem in a new setting. And in particular, this is the expression problem. So the expression problem was posed in the late 90s by Philip Waterloo, and it says that, so basically we want a data type, we want to extend data with new cases, we want to have functions over data type, and extend the function with new cases as well. And they want to do so without recompiling code, and want to maintain type safety. So the goal is kind of ambitious here. But in setting of proof engineering, it's a different case. So we have inductive types. I want to extend inductive type with new cases. We have inductive proof. I want to extend inductive proof with new cases. And then I want to do so without recompiling proofs. I want to maintain logical consistency in the proof assistant. And this is not just academic curiosity. Real-world languages and real-world systems prioritize extensibility and modularity. So for example, we have RISC-V, which is a modular instruction set architecture. So in RISC-V, there's a base ISA, and then we have other extensions like vector instructions and multiply instructions. Another example is MLIR. MLIR is a compiler infrastructure that enables extensible domain-specific compilers. Okay. Now, in the case of certified compiler, this problem is even more pressing because we have code and we have proof. In last year's PLDI keynote, we have Magnus Marin here, who is the author of KML certified compiler, and he's talking about the need for extensibility and reuse in certified compiler and in proof engineering projects for certified compilers. And also in ComSets, they have noted the copy and paste between IRs and semantics for IRs in ComSets, in the code base of ComSets. And the same thing for KML. They talk about needing a readable diff infrastructure for KML. So the summary here is that we want modular IRs, we want modular passes, we want to cut redundancy and boost clarity between these IRs and certified compilers. So to reiterate, we want reusable intermediate representations, we want reusable passes, and we want reusable compiler extensions. So the goal is kind of ambitious here. So how can we do this? So in this work, we're taking a fresh look at programming. In particular, we're inspired by object-oriented techniques of inheritance and family polymorphism. So basically what we do here is we retrofit family polymorphism and inheritance into the Rocq prover to enable extensible proofs. So this is implemented as a plugin for Rocq today. Okay, let's see how Rocket can solve the expression problem. In particular, we want to do composition and extensibility of certified compilers. So here's imp. In Rockets, modules are called families. So we have something called a unit of extensibility called family. And if we want to extend Rocket with switch, heap, and loop, we do this in a refinement called the trait. And notice here that we don't duplicate the code here. We just extend it modularly. And then we can compose it together to form a new certified compiler. And Rocket is just a simple one-liner. Right? So there's no code duplication, there's no proof duplication, and then there's composition and without proof rechecking. And we also maintain logical consistency. Okay. Let's see the key ingredients of Rockets that enables this kind of reuse. So the first thing is something called F-inductive. So in Rocq today, inductive types are close to extension, which means that once you have an inductive type, for example, this command here, you can't extend it. But in Rocket, we support something called F-inductive, which allows extensible inductive types. So the loop trait, for example, can inherit and reuse the previously defined cases without rechecking them. Then you can also define modular additions to the inductive cases. So in Rocq today, recursion and fixed point and pattern matching is also close to extension. So what we do in Rocket, we have something called F-recursion that allows us to extend and reuse cases of recursion and pattern matching. So we have the compilation function here, and we can reuse these cases without rechecking them, and we can modularly extend it to support new cases. So the last ingredient here is something called F-induction. So inductive proofs in Rocq as well are close to extension. And what we do in Rocket is that we can have something called F-inductive, where you prove cases, and then we can reuse those cases just like F-recursion and F-inductive. And the key idea behind Rocket is this. Every family member is an implicit extensibility hook, which means that the meaning of a family member is late bound, is not hard-coded to the particular family it is in. And aside from F-inductive and F-induction and F-recursion, nested families are also implicit extensibility hooks, which means that if you have a nested family called IL, which represents an intermediate representation, is also late bound. So the meaning of IL is not hard-coded to the imp family. So nested families are late bound. So let's see how this late binding can help us in modular IRs and ILs and passes. So imagine we have an underpass compiler that compiles IL1 to IL4. So in the first pass, we're removing some feature X, we're removing some feature Y, we're removing some feature Z, and we're adding some construct W at the end. So clearly, because these passes are very similar, they share some common structure between the IRs and the passes between them. So in Rocket, we can have a base compiler, base IL, rather, that have a common component and common semantics of these ILs, and then the other ILs can reuse the common components. And then we can have a base transformation, and then the other transformations can reuse the common component. And then one cool thing Rocket can do is because of late binding, we can compose extensions. We can compose the passes together and get a fusion, which is just a single tree traversal. So we avoid long compilation time through late binding of the S families. Okay, we've seen Rocket so far. We've seen how Rocket brings extensibility and reuse certified compilers. We've seen the key ingredients that brings about Rocket's expressive power. So let's see how Rocket works. So we know from OOP theory that the essence of inheritance is self-parameterization. So what we do in our implementation is that we compile the implicit extensibility hooks in Rocket to explicit self-parameterized modules in Rocq. So basically, we follow this principle quite literally. And then our compilation is also incremental to support interactive theory improvement in Rocq. So let's take a look at an example. So here, for illustration purposes, I've nested the com inside a nested family called IL. So we can see that we compile this IL, and we have two parameters which represent how nested it is in the family. So we have parameters that represent the self-parameterization of each family. And I'll do a similar thing for F recursion, and do a similar thing as we compile the function. So one important thing here to note is that the self-parameter represents the typing context of a family. The typing context is the previously defined cases of a family, and this allows us to have a well-founded open fixed point when computing the fixed point. So here's what we do. When we close the family, we reuse all the cases and we take a well-founded fixed point of these self-parameters. So previously, we mentioned that we compose extensions in Rocq without code duplication. So let's see how that works. So take this extension we've developed, and then we'll compile each extension's compilation function into a parameterized module. And then when we want to compose them together, we use the Rocq include mechanism. So this way, we reuse the code that we've previously generated without recompilation and rechecking proofs. So we've seen the language design of Rocq. We've seen how Rocq works. Let's try and scale Rocq to a larger proof engineering project. So in particular, I want to scale it to a composition and extensibility of certified compiler project. So let's start with our base imp compiler. Then we extend it with different features. For example, we extend it with heap, switch, loop, external calls, intrinsic calls, function calls, structures, and union. And then we can compose these features together to get a compiler for an imperative language with all these features together. And it so happens that this compiler is ComSet. And this is intentional because we refactored ComSet to make sure each of these features is modular. So we've taken ComSet passes. So in the first pass of ComSet from C to C light, we made it to be nano passes, and then we compose them back together. In IRs of ComSet, we have some reuse there between common ILs and common passes. In the back end of ComSet, we also have some reuse between Mac and linear IR. And in the ISA, we faithfully modeled the RISC-V modular semantics in our case study. So Rocq addresses cost-cutting demands for modularity. So we've seen how Rocq does this. So let's look at some metrics about how we quantify this proof and code reuse. So basically, we want to measure the amount of code and proof in terms of lines that it takes to build the base certified compiler and compiler extensions. So for the base compiler, we write it in Rocq and write it in Rocq, and we compare the lines of code. So here we can see that the compiler in Rocq is less than the compiler in Rocq. So this is some setup about F induction and F inductive in Rocq there. And then for other extensions, you can see that the amount of code it takes to write in Rocq is significantly less than Rocq. So this is because of there's no copy and paste in Rocq, and we have some lot of modularity between passes and ILs in the compiler. So Rocq is a generalization of a previous work called FPOP. So FPOP adds an inheritance mechanism to Rocq to enable composable and extensible STLC metatheories. So the key generalization of FPOP is that we support nested families. So FPOP is more expressive. So Rocq is more expressive than FPOP, so we can scale from an STLC metatheory into a certified compiler like Rocq. Another thing where Rocq shines is that Rocq is 18 times faster than FPOP because of some performance improvements we do. Okay, so it has some limitations as well. So Rocq is currently slower than Rocq. We need some more proof automation, and we need some more language features like extensible records. So we've seen language design and implementation of Rocq. We've seen the expressive power afforded by Rocq, how it allows the monolithic certified compiler to be modularized. So our design of Rocq was guided by a real and important use case, which is the construction of certified compilers. Proof compilation is fast, which makes Rocq a practical tool. So we hope that this will be a step towards large-scale modularity in the PL community. Thank you.
Okay, so we have time for some questions. Please come up to the mic.
Actually, I have a question myself. So I guess so here you use some modules to solve the expression problem, right? And then in the data types a la carte paper by Philip Wadler, they solve it with type classes with minimal metaprogramming overhead. So I wonder, how would you compare your approach to their solution with type classes?
So there are two solutions in general to expression problem. So the first class of solutions is linguistic solutions, and second class solution is like library solutions. So linguistic solutions add new features to languages to support and solve the expression problems. So library solutions use the machinery already present in the language to solve the expression problem. So I think it's a trade-off about how you want to solve your problems. So as PR researcher, I think linguistic solutions are more elegant.
But Rocq has both module system and the type classes. Do you try solving this with type classes?
So it's just about abstraction, right? So we want to higher level of abstractions, in particular inheritance. So inheritance, we can, do things in a straightforward way and say this extends this thing, and then it's straightforward, right?
Okay, thank you.
Hi, so I actually had two questions. The first question is I wanted to ask about the proof experience. So can we prove it like directly at the level of Rocq, or will we need to compile it to Rocq first and then prove with it?
Yeah, so prove directly in Rocq. So because our compilation is incremental, we're on par with Rocq as well.
So can you do like structural induction directly on F inductives?
So F inductive does that for you.
Oh, okay. And the second question, have you tried benchmarking your refactored compiler? How does it compare to the original compiler in terms of speed?
Yeah, so because of narrow pass fusion, we recover the same performance back. So you can check more about it in the paper.
Thank you.
So how do you verify that like your different, this is a very modular system. How do you verify like the different features you're going to add modularly don't like interact with each other in a negative way that like invalidates some of the proofs you'd want to make about the language?
Okay, that's actually a very good question. So in OOP terms, this thing is called feature interaction, right? So when there's feature interaction, Rocq generates new proof obligations for you to prove. So for example, if you're doing STLC and you combine like a fixed point and ISO recursion, it generates new proof obligations for you to prove.
It's really cool stuff. I was wondering, your examples, does it also support extensibility of arbitrary inductive families with indexing and everything?
Okay, we don't support indexed inductive types.
So it's extensibility of typically the syntax of the language, not necessarily of some relation over it.
Okay, actually, we support nested inductive type, but we don't support. So we support indexed inductive type, but we don't support parameterized inductive types. So I know parameterized inductive types can be simulated by indexed inductive types.
Usually at the loss of a universe level, right?
Yeah.
Is that ever a problem?
In our case study, we don't run into any problems about that.
Okay.
I have a question also. In the presentation we saw yesterday by Owen, he showed how he extended an existing compiler, Bedrock 2 compiler, by adding leakage traces. So that's an additional state element. Whereas in your presentation, you were only showing the addition of cases to inductives. But could your approach also support the addition of new state to the semantics?
So I guess states are represented by like a record, right?
Yes, exactly.
So that would require like a new language feature to have extensible records. But it's possible with polymorphism.
But that's future work?
Yeah, future work.
Nice. Do you have more? Simon, you can already set up, but while Simon is setting up, we can also take more questions if there are. Otherwise, let's thank the speaker again.